Good day students, and welcome to a new nugget on biomass for energy. By now you are well familiar with the most fundamental properties of biomass, and you also know how the raw biomass can be transformed into a biofuel. You also know that the fact that something is a biofuel does not necessarily mean that it looks like a piece of wood. Instead, it may well be a chemically well-defined substance such as methane or dimethyl ether, and it may be solid, liquid or gaseous. But one thing is common to all types of fuels, fossil or renewable, pure substances or mixtures, and that is that the energy in them is chemically bound. And that means that we have one and only one process through which we may extract and utilize the energy, and that is combustion. Look at the first page of the rest chains training material and focus on the customer demand. You will notice that customers may very well demand process heat, and that this demand has been split into several temperature intervals. This is because different temperatures put different demands on the process itself and also on the fuel to be used. Now look at the Busy Plan Handbook Chapter 4. Looking at the contents of this chapter, you will see that about 2/3 of it are about how the energy can be extracted from different types of fuels and about different types of plants. So the next nugget will concentrate on combustion temperature, and then we will look at different types of processes. But first we shall look at the combustion process as such from the most simplified perspective. Looking at the top of the page, you will see that the combustion process basically can be regarded as the photosynthesis reaction in reverse. So the combustion reaction is to take a fuel and, in most cases, use the oxygen in the ambient air to oxidize the fuel and thus release the stored energy in the form of heat. This heat will then be present in the combustion products, so they will be hot. And the combustion products are usually gases. So the first thing one has to do to understand the basics of combustion is to be able to set up the general balanced stoichiometric combustion reaction. In this slide you see how 500 moles of hydrogen gas require 250 moles of oxygen gas to release 120 megajoules and to form 500 moles of water vapor. If the combustion used air instead of pure oxygen gas, it would look like this. So now there is a nitrogen ballast. And the same thing happens with ethanol combustion in oxygen and in air. But here I removed the energy just to keep the reaction on one line. As you learned in the previous lesson about thermochemical conversion, there is a process called pyrolysis. During pyrolysis, some of the solid biomass constituents are degraded and release a gaseous mixture of hydrocarbons and other gases when heated. As you will see in the Busy Plan Handbook appendix concerning fuel analysis, we call this fraction of the solid biomass volatiles. At combustion temperatures, will the volatile components remain gaseous, but if cooled, at least some of them will condense and form tar. Looking at the combustion process this way, we find that it becomes a series of sub-processes, the most important of which are the drying, the pyrolysis, the gas phase combustion, and finally the solid phase combustion. So what is ultimately found in the combustion products, assuming a complete burnout so that there are no unburnt components left, is water vapor from the fuel moisture, from volatiles combustion, and from char burnout, plus carbon dioxide formed by volatiles combustion and from char burnout. When it comes to ash, it will be found in the gas phase as well as in the bottom ash. As you saw from the previous stoichiometry slides, will sulfur be oxidized and found as sulfur oxides in the combustion gases. As for our other emissions formed, like nitrogen oxides, hydrochloric acid, aerosols, etc., you are referred to the Busy Plan Handbook appendices and to other sources. There is one more thing to be mentioned, though. One of the most crucial things for an environmentally friendly combustion is the quality of the mixing between combustion air and combustible gases. The combustion aerodynamics, the mixing, or the turbulent structure, is, together with the temperature, the two factors setting the limits for the chemical reactions needed for a complete burnout. So once the microscale mixing, molecular scale mixing that is finished, and supposing the reactants have a proper temperature, then you only have to wait and the reactions are likely to occur. Therefore, the common saying is that combustion depends on 3 T's: time, temperature, and turbulence. But for you who only need a short introduction, it will be enough with simple stoichiometry. So now go on to your homework.